Today's section I will start with the title entitled as a hybrid quantum machine learning framework for radiological image analysis. Today's section explores the interaction of the medical imaging, artificial intelligence, and quantum computing. The central theme is how the hybrid quantum classical mechanical machine learning artists may be enhance the radiological image analysis towards a better diagnostic probability. Today's session outline, as this 90 minutes lecture I divide into 4 parts. The first part will cover the foundations of image processing. The part 2, what are the clinical challenges we have, how to overcome by using conventional AI, followed by the challenges posed by the conventional AI. Session part 3 will be advanced AI and how that will be combined with the quantum approaches to enhance the imaging radiographic image analysis. And here the fourth part is the what are the features, scope, what are the risks, opportunities in the field of quantum machine learning, followed by the summary. Come to the introduction. First, we need to look for the what is the importance of the medical imaging. Of course, last 2 days, the professors might have gave a overview what is medical imaging and how it could be, what is the need of the technology which is available like machine learning and deep learning techniques to apply the medical imaging, especially. Of course, we will find so many applications of the medical ML and DL. But come to the medical point of view, you must see the project. It's a brief scenario. Let's come to the while diagnosing any disease on the human being. The most of them is one of the scanning facility. For example, let's take a CT scan. Might consist of around 500 plus slices. Come to the MRI study, it consists of thousands of pictures data points. That means if you consider the country like in India, altogether it's generating a huge amount of data. That is one of the data which is available. That means huge amount of data is available. But however, to diagnose any disease, you are supposed to extract the useful information from the huge amount of data. That means most of the data which is available is useless. That means you have to extract the useful data by the doctor or by the radiologist to diagnose it. As per that means if you see another scenario, one is the huge amount of data, first point. If you another scenario, that means the radiologist is a normal and let's say multi hospitals. That means per day, that means 200 to 300 scans per day should be interrupted. As you know, as being a human being, it leads the missing noodles. That means sometimes that may be overlooked. That means small tumors are overlooked. That reveals based on his statements, based on the summary given by radiologist, that doctor will take the decision to make a decision on to diagnose and suggestion of medication. That is one of the challenge you are facing as on today, because the population going on increasing, there is scarcity of radiologists. But this is where IIA enters. Of course, as on today, present AI is applied to the medical imaging, but there is a lot of limitations. As you know, the accuracy and the reliability is one of the key factors. If any misleading is cost the human life. That's why, unlike other fields, the application of AI in the medical imaging is one of the challenging tasks. And this way, people are going to add to the quantum concepts to the existing machine learning, which is called as a hybrid quantum machine learning, which leads advanced precision, faster detection, and expecting better results. As you know, a simple definition of medical imaging, That means the is concerned with the interaction of all forms of radiation with the tissue and extract the clinically useful information, usually dependent in image format. The data is always image. That means the radiation source interact with various forms of biological tissues in a body. Based on the interaction, based on absorption and something like that, there is a if anomaly found, that will be reflected in the image. That means what we are calling it is a raw data. As I mentioned, the raw data, that means as like if it is CT image, we will find the 500 plus slices. However, that means we need the valid data from that 500 plus slices. That means the best results are the required information we found in a single slide, something like that. That's where the raw data is converted into useful data. But these are various sources we have. You will find in a normal in CT and MRI or ultrasound with the different types of images available. I mean, to make use diagnosis of a human any diseases. Right. Now let us see what you are looking for from the raw data. As I mentioned, you have to interpret the given data such a way that means the unused, I mean useless information should convert into useful information. As in a broad sense, I can say like this, because the raw data may contain a huge amount of useless information. Among that, you have to convert into that can be created as data, that is useless data. That means you have to get the information. That's what you have to get the information by applying image processing. By studying the information, we are able to, diagnose the disease. Like the signals. That means the image should convert into when it gives the qualitative features. Like there may be shape or texture based on that, and the qualitative features like what is amount of quantity. That means it requires the space, temporal modeling to get the patterns that may be in both aspects, qualitative as well as quantitative. Both it is necessary. That means we qualitative sense like a shape, quantitative sense the area that is occupied by the area. That means the measurements we need to get. Like as I mentioned here, the quantitative feature is 15.2 is a quantitative nature. Whereas qualitative means suggested it will tell us how it looks like, what is structure of that. Of course, both are very, very important while diagnosing this one. This is a conventional data pipeline. This conventional data pipeline that the signal acquisition, signal acquisition, that is the raw data, as I mentioned. That means it should be reconstructed by using some techniques. Then you have to go for the processing of the raw data. And at the end, the raw data from that image, you have to extract the single image, which should give a qualitative as well as quantitative information to analyze that. That means the where interpretation, how to interpret the data, stays where the AI intervention is most impactable for clinical decision making. Of course, the clinical decision making is a tough job without getting the actual information. Right. Come to the yes, there are a lot of doctors available. That means radiologist given to the report that is given to the doctor. Doctor will take decision. Both. There is a lot of impact of radiologist as well as doctor while taking a decision, clinical decision making. However, as a human being, as I mentioned, there is a lot of limitations. That's why I mentioned the statement like this here. Man is an imperfect data processor. That means once the malfunction took place while writing a report by the radiologist, that based on same report, the doctor will take a clinical decision. If anything went wrong by the radiologist, one aspect by writing a report, On the other aspect, interpretation of the report given by the radiologist, by the doctor also one of the aspect, because both are human beings. There is human limitations. That is, as I mentioned, is a fatigue. There is age factors. That means there is a work stress. There's a lot of things. A lot of things may lead. Data will not be processed properly, even though the data, that means the MR scan, CT scan, machinery data available. This data is good, but you are unable to interpret properly because he is a human being. Come to this, while taking clinical decisions, what are things we need? First, we need the right information, is the right time, in a right format. By combining all together, the all together leads to sound clinical decisions, depend upon the convergence of all these three factors. All are very, very important. However, as I mentioned, humans are very sensitive to the quantity and organization of the information, because we commit to fatal errors when a data is too voluminous and sparse, because they are supposed to interpret the data by the human brain. Now, once the errors are omission, what happened is there is a mislead of critical events may simply because they fail to take a decision. The malfunction, mal decision, the imperfect decision of the clinical decision will leads the cost of life. That's why you need to pay much attention applying any technology, especially in the case of healthcare. That's a very, very important point while applying any technology, like may not be anything, what technology or what algorithms are applying. That means you need to pay much attention because it's cost of life. Yes. See, this is complete this overview where the technology needs, where the way needs of AI, what the present changes or challenges you are getting. Yes, the modern healthcare technology systems generate massive volume of data. That means in terms of MRI scans, CT scans. That means sequencing and biometric information, electronic health records, patient history. As you know, in addition to the symptoms from the MRI scan and CT scans, we need to consider the patient history also while taking a decision. I think all of you might know. That means that there's a lot of information you are supposed to analyze before going to the clinical decision making. That means the core problem is clear. There is a huge amount of surplus of data, and there is a display of number of radiologists available to interpret this data. That means the growth in medical data far exceeds the availability of trained clinicians who can interpret it efficiently and consistently. That is one of the challenges you are facing. This creates a work bottleneck, delays, and increased cognitive burden to the healthcare professionals. Studies suggest that the intelligent AI integration can improve the workflow efficiency by 20 to 40%, particularly by the automatic routine tasks assisted in a complex case analysis. However, that means the goal is not replacement. That means AI is not going to replace the human being. Make a note that the goal is only clinical decision support, not a replacement. As AI is a augmentation tool that enhances diagnostic precision while preserving the human judgment. This is a very important point. By seeing all together, let me summarize this slide. This is where the technology need. The healthcare data explosion is not just a technical challenge. It is a clinical imperative that necessitates the intelligence, scalable computational solutions. This where the goal is the technology going to assist the, gives the clinical support, not a replacement. Yeah, let's see where the technology you're going to apply. What is it? Before that is analyzing the data by completely humans by using that's manual analysis before that. After that, let's see this. The primary job of a human being, that is what you are calling it as a radiologist, is classification, segmentation, detection, and followed by the programmatic modeling is necessary. That means what you are looking for. There is transformation from manual review to the automated with high precision pathology detection. This is where the ML and DL algorithms plays a vital role in a medical imaging. That's what I think day before yesterday and first 2 days, what the professors covered, what is the importance of the deep learning in the healthcare technologies. Yeah, this is the conventional approach. That means where during the processing of that images, like we have input image by applying ML and DL models. That means we can diagnose this. Like for example, let us take a tumor is detected from the given image. Here, the CNNs automatically let the hierarchical features. You can use the CNN or resonate. Low level edges and textures, in the mid level shapes and contours, high level pathology, and if specific features. They outperform the traditional handcrafted features also. However, the AI requires, like deep learning and machine learning, requires large data sets. That is one of the big challenge we are facing. High computational resources. That means a lot of hardware required, consumes a lot of power, needs more and more space. Like you need a GPUs. That means you need to organizing is very complex structure. As you know, techniques as I mentioned here, machine learning, that is SVM or random forest, and deep learning is CNN, USNet. I think they might be covered previous lectures. What are the key applications? There's a brain tumor detection, a stroke classification, lung cancer. Before ending section, I will take one case study. How could you apply the QML for stroke classification? Now, I will take the example for that as a case study. But these are things we need. In the case of classical learning, classical AI. Yes, see, as I mentioned, these are what are the limitations? As I mentioned, it needs large data sets. But using the large data sets is a high computational cost. The first cost, right? And if you consider the low data set, the accuracy will come down, and there is a overfitting. And come to the as ethical point of view, one of the big challenge in the medical area is data privacy concerns. Then one can look for make a data set is being a reliable data set is also one of the challenging talks as a research point of view. Instead of analyzing the data, data available in a market, in the market, one can look for a good data set, a reliable good data set, which is used for training, because that will play the vital role in the case of machine learning and deep learning, as you all of you know. Even of QML also, because I am going to deal with a hybrid, not a pure quantum. I think it is also data set which plays the vital role. And one of the biggest challenge in the AI, the black box view. I think some of you might be heard about the term. In a deep learning, machine learning, and hybrid technology, there's a lack of explainability because we don't know what is happening inside. You are giving the input and you are getting the output. We are not sure what is happening inside. What is it thinking? This is a probabilistic outcome. Up to what extent it is true, up to what extent is reliable, is a question mark. Till now, the situation is like that. One of the challenge in AI is a black box view. That means the people are looking for the explainable AI during this. Explain how that means that should be addressed. I mean, the algorithm should address. I mean, you should understand what is really happening inside that. But then only we'll assess whether the output of the model which is trained by you is reliable or not. Because unlike other fields, this 1%, 2% error is doesn't matters. But in the case of healthcare, might it's not like that. That means costing of is cost of life, as life is, as I mentioned, because you are dealing with human beings. These are the some. I mean, the key limitations of classical. One thing is you need a large data sets that cost high computational power. That means one is data privacy. That means there is a, I mean, there is ethical rules and regulations as per medical regulations. That mean medical. I mean, the hospitals doesn't have a right to share the information related to patient. That's why I mentioned one can look being a faculty members in the case of research area. One can look for a making good data set is also is good publications, right? Come by discussing all these things. That means by discussing all this, there is a we can overcome up to some extent. We can overcome some extent by shifting by shifting the classical computing to the quantum computing. As you know, the computation made by the classical in terms of classical bits, in the case of like all which are using in a daily life is as you know, digital information like zero and ones only. We are looking for quantum computers and quantum computing, in which instead of binary bits like 0 and 1, we are going to make use the qubits. See, what is the basic idea or basic difference between them is in the case of classical bit is a deterministic. That means exists one state in a time. That means the classical manner, that means one can predict. For example, let us take a case. I can find the age of any human being by knowing the date of birth. What is the age of today? That is classical theory. Whereas quantum theory, up to what extent he will be alive. I mean, can't predict, no? That's called as a probabilistic. That means completely predictive nature. In the case of quantum computing, of course, I'll cover the basic principles of quantum computing like superposition and entanglement. That means in the case of quantum computing, the output is predictive nature. It's unlike deterministic. As I mentioned, for huge data sets, large amount of time it will take to train the model or architecture, what do you call. The beauty of quantum computing is it supports the parallel computing. That means the time for processing of the for processing of anything will becomes small and small. That means we are moving the computational, move from binary processing to multi-dimensional quantum states to overcome that computational limits, as I mentioned, that huge data set. Yes. See, this is by seeing that we can understand what is the need of the quantum computing, especially in a healthcare. As I mentioned, you need a lot of accuracy, and moreover, if you compare with, for example, let's take one classical bit, but is able to work with only one state. If I use one quantum bit, we have two states simultaneously. That means 0 and 1. I'll come to that. What is the qubit? What's superposition principle? And next slide. Before that, let's try to understand what is the importance, what is the basic difference between normal conventional computing with the quantum computing. In the conventional computing, as I mentioned, we are using a, let me go back here, the classical bit. Where here you are using a quantum bit. This quantum bit is continuous 0 or 1, it's 0 or 1. Whereas here, in the case of classical bit, only like by seeing this, with the classical bit, you can able to process one state. Whereas in the case, if you use the one qubit, that we can process the two states simultaneously. If you keep on increasing, like 2 qubits, 4 states simultaneously, for n qubits, we are able to get the 2 power n states. So mathematically, I can say like this: this exponential growth allows the quantum computers to process the large state spaces efficiently. Then automatically, the processing speed will goes up like anything in exponential growth compared to conventional computers. That is the beauty of quantum computing. Yes. Let us see, as I mentioned, the qubit concept is based on the superposition principle. It can be defined as it can exist multiple state at once. Read carefully. It's defined as a quantum system can exist in multiple states, unlike classical bits. But the system remains this state until it is observed and measured. Once if you measured, after measurement it ends, it collapses into a definite state. That means maybe 0 or 1. However, it is a bit confusion, but the qubit concept is like this. It's based on the superposition. It consists of both bits simultaneously. After measuring, it becomes 0 or 1. That's what I mentioned. The collapse is like after measurement, it collapses to one finite state. During processing, it contains the superposition principle. That's where the parallel computing. I will come with one example. Right. See this. Imagine if flipping a coin, but instead of landing heads and tails, can coin exist at both heads and tails simultaneously until someone looks. Just try to correlate with this scientific definition what I made previous slide. Like the quantum state can exist multiple states. Like multiple states, and then let's take a coin having both head and coils, right? Just it's a flip. That may be, of course, outcome will be head or tail, unless until someone looks. If it is head, the automatic time will not be there, no, like that. That means 2 will be simultaneously exist, 1 and 0 will be present. And let's go for another example, like no, clockwise and anti-clockwise until its spin is measured. Yeah, what is impact of quantum computers? As I mentioned, this enables quantum computers to process the vast combination of data simultaneously. And another example is, see, let us assume a case to understand the superposition principle. A cat in a box. Assume that the box is closed. A cat in a box. But we are, that may be two states. That may be live or dead. That is what you are calling it as a superposition. until someone open the box, because assume that the box is closed. Assume the box is closed, right? Of course, cat inside, but you don't know whether it is closed or sorry, whether it is a live or dead until you open the box. But that is the another physical example for a superposition principle. This computes the parallel computing. As I mentioned, is combination of data. Another concept we are going to use is entanglement. That means two bits are interrelated or entangled, means linked together, such a way that by knowing the status of one bit, one state, we can say like this, we are able to find other particle states without measuring that. That means the measurement becomes off. Let's say correlate with this. Let's say two or more particles become entangled, means measuring their states are linked. That means the change in one particle state instantaneously affects the other, no matter how far it is. That means, yeah, let me conclude here. In the entanglement means information about the one particle gives information about the other. That means one measurement is enough. One measurement is enough to know the status of them. I'll go with some example, right? See this. Let us take an example here. We are spinning two coins. The condition is that it is always opposite of it. I repeat, we have two coins. We are spinning two coins that are always opposite. That means if one is heads, other must be tails, even if they are on the different planets. That means the distance how much far away. The distance is not a matter. Simply by knowing the state of one, if it is head, automatically other will be tail, and vice versa. That means the measurement of the data, the measurement of the state becomes off. But that is also one of the parallel computing concept, right? Why it matters? What is the importance of that? Yes, suppose we have two qubits. According to entanglement, by knowing the one status of the one qubit, automatically you know the other qubit status. That means measurement becomes off. Then how it is useful for the medical imaging is it allows complex feature interactions, parallel correlation analysis, enhanced pattern recognition, unlike normal classical computing. Of course, in terms of machine learning, it helps to model linear dependencies between the features. But that's why the quantum computing is enhance the medical image analysis, right? But before entering into the real quantum computing, let's have a look on is one of the important slide. Those who are looking for the working towards the quantum computing, the NISK stands for the noise intermediate scale quantum era. At present, yes, people are almost all. There is one of the upcoming technologies, quantum computing. Of course, this. But what are the present status of the quantum computing? Up to what extent it is applicable to the real world applications and as a common people? Right. Let us see at present that the quantum hardware especially operates in the very low qubits count, that is 50 to 100 qubits, and moreover, these are not fault tolerant. That is one of the key challenges we are facing. They suffer from the noise quantum gates and limited coherence times, meaning computation must be shallow and carefully optimized before quantum states decode. That means that is what we are calling it as black box view, with a limited scope to understand what is happening inside. As a practical example, let's take such as IBM cloud accessible quantum computers allow the experimentation such as research, but they clearly reflects the hardware constraints. Because of these limitations, full quantum machine learning pipeline, my expression of high dimensional imaging is not at all feasible. Therefore, we are looking for the hybrid approach. It's not think is it innovative, it is realistic, where we are combining the classical concepts, a classical approach to the quantum approach. It acknowledges the hardware constraints while strategically integrating the quantum components where they add the value. I can summarize the NSK era demands parameterism and hybrid architectures that should represent the most significantly ground path for. But these are the challenges we have. Based on that, why you are looking for hybrid instead of pure quantum machine learning, quantum computing? Why you are adding the classical processing with quantum computing? Both are why you are making a hybrid mode is that means combining the classical ML and classical deep learning techniques with the quantum computing in the NIST era. Means where there are a lot of hardware limitations while implementing the pure quantum computing. If you see the diagram, how these two are mixed together, it tells us we are not replacing a classical system with a quantum ones. That means we are integrating their strengths. That means the strength of classical processing and the strength of quantum computing are making use. Like let's come to the classical pre-processing is concerned. It able to process heavy computational work, extracting the hierarchical features from the high resolution medical images and converting into compact meaningful feature vectors. That means this step ensures the scalability and stability. On the other hand, as quantum is concerned, it operates on this reduced feature embeddings. That is, quantum circuits provides high dimensional representational capacity, enabling the complex feature interactions and potentially richer decision boundaries for a classification point of view. Given the current hardware limitations, limited qubits, as I mentioned, limited qubits, noise and decoherence, fully quantum pipeline is not at all feasible. Therefore, hybrid strategy is practical and optimized for the art to satisfy the that NISC. That means the classical model handles the large scale data processing, whereas the quantum circuit enhances the nonlinear feature representation and classification. In essence, the hybrid approach is scientifically grounded. I implemented a solution that bridges the present hardware constraints, expert the quantum advantage in a medical AI. This is the reason behind why you are combining classical preprocessor with the quantum processing. Even I stated the quantum computing is superior performance in terms of classical computers, but you can't replace. But this is a broad view of that means hybrid quantum machine learning architecture. That means classical layer followed by quantum layer. The first classical layer, the first part, that left side, The classical layer, the medical images are processed using CNN or reset to extract the high level features and convert into future vectors. Then these features are then passed to the quantum layer where they are encoded to quantum states using techniques such as amplitude encoding, and a parametric quantum circuit process parameterized quantum circuit like polygate, jet gate, it process the information and leverage the quantum superposition and entanglement to model the complex feature interactions. By using that, we are able to measure the after quantum measurement, the resulting problematics are used to finally classify such as is a tumor is present or not. Overall, this hybrid framework combines strengths of classical deep learning and quantum computing to enhance the decision making in healthcare applications. Right, this is where the computing, it's the classical bit versus qubits, where the computing takes place. In the left side, you see the classical bits are restricted to binary at 0 to 1. The classical computation operates in a discrete vector spaces. Even in deep learning information is ultimately encoded in a deterministic numerical representation only because it supports 0 to 1. Whereas in the case of qubits, where it satisfies the superposition and the entanglement principles, that means we take the superposition in states like 0 and 1 simultaneously. Instead of single axis state, qubits represented in a allowing the continuous probability amplitudes. When the multiple qubits are interacting through the entanglement, the system spans exponentially large Hilbert space. Then what is the advantage you are getting by using this? By using the quantum states is the quantum states naturally operate in high dimensional Hilbert spaces, enabling the representation of the complex nonlinear correlations that may be difficult to model in a normal conventional spaces. That's one of the advantages. Let me confine it to the medical imaging is concerned, because we are dealing with medical AI. For medical AI, the simplest potential advantage as modeling in a patterns in the radiological and pathological, but especially where the decision boundaries are slightly non-linear. The key set of this, the QML leverages the superposition and entanglement process, exponentially large gives the large Hilbert space. This leads the capture the complex nonlinear correlations in a medical data that classical vectors are missed. That's the advantage you're getting if you make use the you represent the data, structured data in a Hilbert space. Yes, these are the algorithmic engines which are going to use the case of the quantum machine learning. First one is the variational quantum circuits, popularly known as EQs. These are the parameterized quantum circuits, but trained to a classical optimization loop. That means similar to like in conventional neural networks with back propagation in the neural networks. That means circular parameters are iteratively updated to minimize the cost function. That means the key EQs are the most practical approach in an SCADA from the backbone of the hybrid models, because with using the lower bits, we are able to model the system. That means you can optimize the parameter. You can optimize the parameters. That means that the amount of time to need the iterations will come down. And to come to the quantum kernel methods, the classical data is embedded into as I mentioned, high dimensional Hilbert spaces using quantum features here, maps the data into high dimensional Hilbert spaces to find the separation of boundaries. That means for classification of the data. Now, if you see the concept, what it behind it, this section the classical kernel trick into the quantum regime potentially of richer representation capacity. The capacity is enhanced because we are getting a lot of space to implement the same. Lastly, now quantum neural networks. These are the quantum analysis classical network. This is similar to the classical network. Here you are utilizing the superposition and entanglement to process information while still evaluating. They aim to model the complex correlations beyond the classical architectures. In summary, these three regimes, namely that VQC, quantum kernels, and the QNNs from the fundamental computational strategies drives the research in a quantum mechanics. One can focus how to implement how to map, in fact, the quantum, as I mentioned, the classical features extracted by the classical deep learning, machine learning models to the quantum circuits. Like quantum kernel layers and QNNs, there is feature. Some of the algorithms which people are working in a QML. Yeah, this thing, of course, seems to be in the last previous slides has shown you in the case of hybrid model, the standard workflow. To better understanding, I frame it like this. Yes, you see the complete overview, the workflow of the hybrid quantum and classical model. Like, so of course, as we have input, that means image captured by the any like CT scan or MRI scans. Given to the classical technique to extract the features. Yeah, this way the vital role, that is, as I mentioned, the encoding the data into qubit mapping. The features extracted with the classical, because it is able to, like if it is the CNN, might is able to handle the large amount of data. That means, let's see the step-by-step procedure what they are doing. We begin with like input. Let's say CRI or MRI scans. That means the CNN performs the feature extraction and the overall dimensional reduction, because according to NSQA era, there are limited qubits. Still, people are working less than 100 qubits. That means we can't map the high dimensional data to the qubit, because the qubit number of qubits are very, very less. Still, people are working less than 20. Even though IBM climbed to 50 to 100, it's not really realized till now. If you see the research papers, the people are working 4 qubits, it hardly 16 qubits only. But that's why the CNN perform the feature extraction, and there is a reduction dimension. That means the first part, the classical crunch, as I mentioned, is do the intentional processing. That means transformation the high resolution image into compact without losing the exact information what the image contains. That means it is informative feature vectors. As I mentioned, starting itself, there is huge amount of data. Among that, there is a lot of stuff is useless. You are trying to get the useful amount of data. That's one way the classical crunch will do that. We'll extract, what I mean to say, informative features. That means use that will separate that useless data from the raw data. That is the basic idea of the classical crunch by using CNN. That means it transfers the high resolution images into the compact informative features. That means without losing any information. Next, come to the encoding point of view. As mentioned, there is data to the qubit mapping. That means the extracted classical features is encoded into quantum states by using it such as like as angle model, angle encoding or amplitude encoding. And that's why the features extracted in the classical should be very less because the number of qubits available are limited. This way, the gap, I mean, there creates gap, the bridge creates bridge between the classical and quantum domains. Of course, at the final stage, I mentioned that we use that means the quantum layer, which performs the optimizing the region boundaries in a high dimensional Hilbert space, which supports the like because of superposition entanglement, you are getting Hilbert space. Then use the output is clinical diagnosis like this. I mean, by seeing this, what is the idea behind combination? I mean, combining the classical and the quantum technologies altogether, we are calling it as hybrid model. Is the classical layer handles a large scale information feature extraction, gives the optimized futuristic data without losing information. Then that refined data is given or mapped to the quantum model, which by satisfying that NISQ era means as on today there is a lot of hardware limitations. If you consider the quantum computing is concerned, but that's where the hybrid model come into picture. Yes, come to the application point of view, where you are going to use this. Of course, almost all data, all type of data which is coming from the medical concern like scanning is image. That may be for any kind of like that may be heart or that may be brain or that may be lung or that may be something like this. That is primary use. That means the technology which you are adopting is to analyze the quantum. Analyze the images. However, compared to the pure quantum, pure machine learning and deep learning approaches which you discussed previous classes, which you demonstrated here, the QML classifiers like SVMs and QEQs and QNNs, like quantum neural networks, quantum machine learning classifiers like variation quantum circuits, but demonstrate the computative accuracy, especially because of small and imbalanced data sets. Yeah, that's one of the key point. With small data sets, it's performing a significant improvement in accuracy. As you all have to know, deep learning is concerned. If the data amount of the data set increases, the accuracy is going also up. However, handling the huge data set is costly in terms of power, in terms of hardware. This is one of the beauty of the QML, which supports the small data set. But for using small data sets, you are getting the on par with sometimes more than accuracy than normal deep learning and machine learning techniques. Yeah, another thing is I think you might be aware of that. That means imbalanced data set is one of the big challenge. I will discuss later. That means if you see this one, like yes, but this is where before going to the actual what are the challenges we have, let's go for the case study which I take, step by step process to our better understanding. Let us take an image that is input from the problem statement here is the objective is early detection of ingranational RNAs from the brain. But the input is given to the classical crunch where the CNN model is applied. From that, That means after pre-processing, it is applied to the like QNN or ResNet 50 for feature extraction. But the extracted features, I repeat, the extracted features contains the very, very valuable information. That informative features, information like this one, again that is mapped to the quantum circuits. Yes, that means data encoded into the whole data. I repeat, that whole, because huge amount of high dimensional data is, converted into low dimensional data by using the ResNet and QNN, that is mapped with the VQs. See here, as I mentioned here, that I encode into 48-bit qubits only. Best of my knowledge, as on today, people are working with only maximum 16 bits. Still, it is a simulation model. Most of them working on 4 to 8 qubits. That is one of the NSQS era. That is one of the limitations that is of the quantum computing. Here, where people can work on that. While encoding, if you lose any information from the classical to quantum, you will lose the accuracy, you will lose the information. Ultimately, it will show the bad, bad in the sense the accuracy may come down, the reliability may come down. Then this one, after encoding, again that is converted into pre-processing, that is processing of a variation circuit with poly measurement or any quantum states you can use, quantum gates. Of course, I'm not going to go into the quantum gates. After that, after processing, at the end, you'll see the binary classification, that means stroke is present or not. That is stroke is detected or not. Then what is the advantage you're getting by using this this one kind of real-time system which you are using in nowadays, where you can implement this thing in a normal computer. Normally, we can simulate it. If you want to make it hardware, you can make use the IBM hardware, IBM cloud to implement the real-time quantum computers. Up to 48, it's fine. But however, of course, the number of, the encoding the data from classical to quantum computing is one of the big challenge, where people can focus on that. Of course, that is one of the hardware limitations that some people are working towards the, many of them working towards that quantum computing. They are going to implement with a quantum computer with a large number of qubits. That is, of course, another issue. Whereas come to the AI is concerned, this is where this one, what is the real-time application as on today is the present scenario. This pipeline, a framework which is done by me. Right. Let us see what are the, of course, this general terminology, I think you might be familiar with all these things that in my previous talks. That means how to evaluate any system. Of course, these are common factors: accuracy, sensitivity, specificity, and ROC. My notion that by a segmentation point of view, some might be, disk score in the case of segmentation, and ARO series. Of course, here, as I mentioned, where the quantum advantage, quantum system is incorporated here. What the advantage are getting here is a high sensitivity. However, there is a limitation is that, as I mentioned, note here, read carefully. The quantum advantage, which are what we claimed, we are getting the high accuracy with low data sets. I repeat, we are getting high accuracy, or at least on par with the normal deep learning for the large data sets. We are claiming with a small data sets. However, it is demonstrated in a simulation and a a small scale hardware experiments like 4 to 8 bits only. Please make a note. Is one of the challenging tasks. Of course, yeah. If you see the real-time implementation, of course, we can use the I mean, people may think as of now we don't have any quantum computers. How can you implement the quantum technology or quantum machine learning in a normal system? Of course, you can go with this. This is way where you can implement the quantum QML. See here, first consider the top layer, such as QSET or Pennyleaf or TensorFlow quantums. Of course, this is IBM. Most of popular one is IBM QSET. Or for will details, we can Google it and we'll find it. And these are the some of the platforms what I know, or which are supporting towards the quantum implementation. These platforms allows the design of quantum circuits, like as I mentioned, we can simulate the quantum behavior and interface with the real quantum hardware in NISQ era. That's where, as best of my knowledge, IBM only giving the hardware support through cloud. That's up to 4, I think up to 4 to 8 qubits only. Come to the next middle layer, that is classical. TensorFlow, I think some of you might be aware of that, those working on the Python and softwares. The TensorFlow, PyTorch, there are some of the softwares, best of my knowledge, only I claimed here. Some the medical workflows, the hybrid, there is a hybrid pipelines, the classical networks typically generates embedding into the positive quantum circuits. You're supposed to join the first layer, the top layer, middle layer to the hardware like GPU or CPU plus QPU. And the CPU and the GPU for the classical quantum computation, CPU or the GPU, of course, if you want to simulate the large data sets, you have to go for the GPU, where we can freely available in like Google Colab. However, if you want to use the QPU, you are supposed to make use that IBM cloud for execution of the quantum bits. Hybrid training loops operates across the any sources. That means, let me conclude by implementation diagram. Let me conclude. That means the quantum frameworks does not operate in isolation. You see this here, because the quantum hardware is not support the, if you try to simulate or try to implement the direct image process, because there is a large data set structure, large amount of numerical data that cannot handle. That means they are embedded with in nature and classical systems. That means it's supported with heterogeneous hardware. That is all together. We can call it as a hybrid network. This way, of course, people can work on this. No need to bother about the quantum computer. Not look for the quantum computer. Come to the, I don't know how many days it will take to which is hardware available to the common people. It is imagination. Up to how many days? That means no need to wait for towards that. Where you have idea, those people have an idea of implementing the quantum. You can do that by using other. Let's come to the, of course, let me summarize the classical and the quantum readiness. Here the accuracy is concerned. Classical AI is superior. Of course, quantum AI is in the case of large data sets, whereas in the case of small data sets, it is the reversed. That's where I mentioned the quantum computing is giving a superior accuracy for small data sets, because getting the data, small data sets leads low cost of power. Data availability also. Right? Another one is the dimensionality is concerned. Of course, as I mentioned, this Q is a classical K leads the 0 and 1s is a conventional space, whereas in the case of quantum We have a Hilbert space that is high dimensional capability. And the cost point of view, of course, no doubt, the quantum is more cost as and today. Come to the computational cost is concerned. Classically, it needs because it needs a large amount of power angry as I mentioned. But quantum is yet to decide. That means we're still working on in a theoretical point because people are worked hard. The hardware point of view, 4 to 8 bits only. We don't know if you go to the more than 100. Still, it is is under imagination. Up to what extent will be the. Of course, to decrease the computational cost only, you're looking for the quantum AI for limited hardwares. Yes, yeah. These are the some of the challenges. Of course, some of them I might be discussed. First one is the data imbalance. I think people might be aware of those who are working in data. Deep learning and machine learning. The data sets which are available is most of them data imbalance. That means let's take my example. If you take the stroke detection, I have around. I took a 5,000 database. Among that, around 800 is stroke data. Around 4,200 is non-stroke data. That's what you can call it as or you can define it as a data imbalance. However, there is a lot of lot of ideas to make it a balance by making the synthetic data something like that. That means that is also shows the impact, the performance of a given system. That's what I mentioned somewhere. The people can make a good data set is also one of the research tasks. There is huge demand for the data sets as of today because as AI and ML is, demanding is going up like anything. If you see the research papers, some of the papers which is making a data set is making good SCI paper, good paper. That's one aspect. Yeah. Second one is of course, the black box use. I think I gave some of. I think I discussed about this because we don't know what is happening inside the algorithm. Of course, this clean kind of AI and normal AI also this same thing. Not only for quant. These are the key challenges. That's what people are looking for the expandable AI, XAI. Now AI is outdated. Looking for the XAI because unless otherwise you know what is happening inside that, it's very difficult to really rely about the data. Output coming out from the system designed or system tried. Of course, the regulatory hurdles, as I mentioned, getting the data from the hospitals of a patients with a very difficult task as of our medical regularity. Any hospital, best of my knowledge, but doesn't have right to give the share or right to give in the sense share the patient information. Patient information is, I think, it's not best of my knowledge. I'm not sure about that. That's what I think. Of course, ethical responsibility, their mitigation and algorithms accountability. These are some of the challenges where you can focus. First, you can focus on the data set, making a data set also. If your resource is available with you, right? Yeah, is one of the big question. Is what is the reality of, because people are, I think you might be heard, and even you are not working on the QML or DFL and quantum computing, you might be heard in the news channels or media, the quantum computing playing a vital role in future, something like that. Here I'm going to show you up to what extent it is true. Even I claimed my work. If I join, if I combine my that is quantum strategies or quantum principles to the normal machine learning, we are getting best performance. That means terms of like accuracy. But thing is that one is that of course it gives the huge speed, that's super speed, right? Come to the speed point of view. See here, if you see the diagram is concerned, that's the left side is experimental simulation. Yes, last one is the theoretical maximum. If you see the slides which I try to map the colors, theoretically people are claiming yes, max. I mean, it's very good results in terms of speed, accuracy. However, I mean, theoretically, as far as simulation is concerned, where you are, it's around only 20%, but theoretically it's climbing around 80%. There is a huge gap between the theoretical and simulation only, even not in a implementation part. That is one of the challenge. That is what I mean. What I mean to say is up to what extent it is right. Like if I mentioned here, speed up. Of course, we are claiming that it's most theoretical. Yes, but reality is concerned. As I mentioned, according to NSQA era, as of now, as I mentioned, still I repeating so many times, the number of qubits are very very limited because there's a lot of hurdles while implementing more qubits practically. That's why the speed up is only, I mean, most of theoretical concept. Of course, come to the accuracy point of no doubt, accuracy is, I mean, going up. Even my simulation also I showed you compared to normal conventional model and deep learning models. The QML is giving a high accuracy. Of course, this is purely context dependent. There may be chance of I mean, classification reduced feature sets. Then come to the conclusion like that. No, that means QML is not, I mean, currently a general replacement. Somewhere I mentioned starting itself, we are not going to replace that class, I mean, ML with QML. It is add on to the normal ML to enhance the performance in terms of accuracy and other considerations. It is, that's what it is, a special tool for a specific and hard to solve problems where the classical methods are not able to do. That means we can't apply or we can't use the QML models in all cases. We have to look for a where you can focus. That means where you can focus the, I mean, what are the critical areas? Like in medical research, you can go for the quantum computing. One of the key area where you can focus quantum computing, where a lot of I mean, analysis part is required. I mean, iterations are required. I mean, the number of iterations increase, the class also, that means time also increases. If you take the classical computing, it takes one day for iteration. The quantum computing will do within 1 hour. Like that, you are, I mean, the quantum advantage may be applicable for the only few areas because the hardware hurdles as well as cost point of view also. Of course, these are all the assumptions. Up to what extent is true, yet to see. Yeah, another, as I mentioned, no, low qubit, these are large coherence times, noise sensitivity. These are some of the hardware hurdles or limitations of the quantum computing. Yeah, this is also one of the challenge. I think yes, this is one of the key challenge, as I mentioned, encoding data into quantum state. Let's take a classical input which I have is around. Let's take image contains millions of pixels. Where they are going to use the classical mechanism like QNN or CNN, something like that. No, sorry, not QNN, CNN or ResNet to extract the features from the like in a classical input. See this scenario here is millions of pixels. We are supposed to encode with a limited qubits, that's 4 or 48. But this one of the, I mean, challenge. The data encoding is one of the key challenge. Of course, there's, I mean, there is here mentioned different types of encoding techniques. That is amplitude encoding and angle encoding. Of course, because of lack of time, this scope, not the scope of my lecture. That's why I haven't covered that encoding process. As come to the amplitude encoding, it's efficient, but it requires deep and complex circuits, hard for this one. And the angle encoding is bit better hardware friendly, but it's expensive. 10 qubits for the n features. Of course, this is another topic. Is right. What if you are trying to understand, let's see the left side and right side. There is a huge difference. Ultimately, you are supposed to encode that without losing the actual information. Once you lose the information, the output will become collapse. Collapse in the sense that is not the reliable. That's where that's where people have to focus. One solution is increase the qubits. Of course, that is imagination. Up to what extent you will be increasing it, you don't know, right? That means people have to work the encoding technologies, encoding algorithms. Yeah, what is, let's see, impact? Insufficient encoding can generate the computational speed up. That's where, I mean, we need to focus on that. Yes, of course. Yeah, there are a lot of stuff discussed with respect to, like, no, what is the application of QML, all these things, applying the technology to the medical imaging, because to enhance the technology, I mean, performance of the medical imaging for, or improve the clinical decision making, something like that, as I mentioned. However, there is a huge bridge gap between the technology with the clinical adoption. That's see, these are the various, I mean, standard steps in the case of image processing to fill the gap between the, ultimately you are supposed to reduce the burden on the radiologist and doctors. That's what you are looking for, irrespective of what you are doing. That is the basic idea, basic outcome, what you are looking, as I mentioned. I mean, this is a common sense principle as technology is concerned. That means the technology should assist the human being. Here also the same thing. You are trying to assist the radiologist and doctor such a way that reduce the pressure or reduce the, I mean, increase the accuracy to overcome the human error, something like that. But where we need to focus, what are the challenges we have, right? What are the steps we need to focus on that? The first one is the, I mean, standardization, where to focus the development of common benchmarks. That is what is evaluation protocols to ensure the reliability and reproducibility across the studies. That's one of the technology, something like if you are supposed to give a model, that means like it is a I mean, stroke is there or not. That means based on your benchmark only that will decide, because the data available and the image what we have is a different natures, different personalities, different human beings, like that. That means based on the, of course, I mentioned the clinical decision making in additional to that data given, like MRI scan, CT scan, they I mean, doctors should consider the history, I mean, the patient history also. Based on that, we have to make the benchmarks. Well, that is one of the challenge, of course. That's what yet to rely a real time, yet to implement a real time AI and ML system in normally ML system in a medical imaging. Next one is scalability. That means most of the research model work on the down to the sample data, but clinical deployment demands high resolution image processing without loss of the performance and efficiency. Of course, down sample in the sense, I think there is data available in net. That is real. I mean, people are not working, most of people are not working the real time data, which is available in a net. Of course, that net also, that may be related to some kind of people, like people from USA, people or something. No, on the location also matter for the data set is concerned. Of course, there are so many things we need to do, challenges at the end. I mean, of course, while implementing the technology in a medical area, that means a validation. That's what you're doing. Clinical validation is very critical steps. The thing is that where to test it. We can't test directly human being. No, I think you might be aware of that. While making any medicine, that will test on the, like, animals. like dogs and monkeys before onto the human being, because that may cost the life of the human being. No, of course, these are the clinical. I mean, you need a lot of clinical trials that ensure that the models are safe, robust, and clinically meaningful. That means you need to work. I mean, towards all these aspects while convert directly into the gap into the like, yes. But there are some of the research directions where people can work on that. Of course, some of them I discussed already. Yes, one is the data privacy. That means instead of centralizing the sensitive data, patient data, model are trained to locally across institutions, aggregate. As I mentioned, no, the data set is one of the key area. The data set of the USC people may not work with Indian people because the constraints are different. That means taking food or taking food or structure or environmental conditions, all this together. This is very complex in nature. As I mentioned, next one is that expendable waste, because the black box we are supposed to be. That means the operation should be like it's a transparent. One researcher, one doctor could understand. Let's take a researcher, science to understand what is happening inside. Then only they will rely on the what's output you are getting. Of course, the multimodal represents the integration across the heterogeneous data sources and electronic health records. That's what I mentioned. No, it's a past history of the patient also one of the key parameter while taking clinical decision. In addition to data available from the imaging, is not only sufficient. Both all together you have to. That's what you are calling multimodal AI. That's, I think some of the faculty may focus on this also. That means we have to work on the imaging data as well as EHR data put together. Of course, at the end, of course, as quantum computing is concerned, is one of the area where the drug delivery is one of the key parameter. As I mentioned, it supports the quantum processing. Parallel processing. Generally, while making a drug, there are a lot of iterations we need to support. That means it takes a lot of time consuming. Once the quantum comes into the picture, that may save a lot of time. That's one of the major area where you can there is a drastic change, or there may be game changer for the drug discovery. The quantum computing may be game changer for drug discovery. Of course, that's maybe more on science people, not for engineering. I think it's best of my knowledge. Yeah. At the end, let's see the strategic look where you need to apply the classical thing, where you need to apply quantum. However, once again, I'm telling that QML is not a replacement of classical AI. It will be augmentation only. Augmentation only. Right. If you see the diagram, statistically, how it looks like. On the left hand, where we are supposed to use the classical AI, that means if the amount of data is used, that means the CNN able to handle large amount of data, as simple as that. That's why I mentioned like this, hammer and a large amount of data. The quantum AI is able to handle a small amount of data. Once the amount of data is available very small, that means you can more focus, more concise. However, for small data sets, that means we are converting large data set into small data set. For that only, you are using a hybrid feature. That means cloud learning model robust and extracts the, of course, same thing in what I mentioned here. The feature lies the adaptive hybrid structures using classical deep learning for a feature extraction and quantum circuits for the high precision classification. That is the conclusion about this, right? Let me give the summarize of today talk. What I discussed is what is the explosion of the medical data set necessities and AI support to assist the specialists. The problem is the classical deep learning faces the limits in terms of computational cost as well as interpretation of the same. The solution what I proposed is hybrid QML that combines a classical feature extraction with the quantum processing. The case study what we discussed is application of brain stroke and tumor detection in pipelines. The feature, that means then where to focus is the feature is expandable feature learning and expandable feature. AI. Yeah. Yes. Let me conclude. The hybrid quantum machine learning represents a frontier research direction. Of course, with remain under NSQ era, hybrid modes provides the bridge gap between the classical and AI feature quantum advantage. Yeah, I thanks to all the faculty members for patience listening, and once again thanks to management of the Marwadi University and department of the faculty of computer applications and the coordinators and the organized team of the today FTP, that is intention AI in healthcare. Sir, once again, thank you very much, sir.
Thank you, Murali Kante sir, for the insightful session, which is a